Yeah, thank you for the very kind introduction. So as Tom mentioned, I am just putting the finishing touches on a book on logic that I'll show you the table of contents in just a little bit. It's a book that I've been working on since I was a graduate student. I mean, there are actually parts of it that trace back to notes, LaTeX things that I typed up as a graduate student. A lot of it was written during the pandemic. The pandemic was very good for writing. There wasn't much else to do. But writing a book, I found, is a really nice opportunity to return to your favorite topics and think about how to present them. And in thinking about how to present them, you sometimes find that you come to understand them better. Um, and so for this talk, I'm going to be returning some classical results in proof theory from like the 70s and 80s and 90s. And I see from some of the people in the audience that these will be results that are very familiar to you. So you won't be getting a lot of new information from this talk. But these are topics that everybody, I think, should be familiar with and are worth seeing. And so hopefully there'll be enough people in the audience for which, that maybe people who are kind of vaguely aware of these topics, but not fully informed or up to date. And so I'd like to share them with you. These slides are already on my webpage. I haven't done a dry run of this talk, so I don't know about the timing, but I'll keep an eye on the time and hopefully it'll work out well. And as I said, feel free to interrupt with questions and things to clarify. So the general setting of what I'm going to talk about are formal theories of arithmetic. And I will talk about theories in the language of quantifier-free arithmetic. So where you have variables ranging over, arbitrary natural numbers, but no quantifiers over all the natural numbers. Right? So you can say things about arbitrary numbers, but not all of them. First order arithmetic, which adds quantification over the natural numbers. And then second order arithmetic, where you can talk about sets of natural numbers and quantify over them as well. And particularly, I'll be telling you about primitive recursive arithmetic, which is a formulation of what Hilbert and Bernays meant or might have meant when they talked about finitistic reasoning. A fragment of first order arithmetic called I single one. A fragment of second order arithmetic called RCA naught that's designed for reasoning about computable sets. And then a fragment of second order arithmetic with an additional compactness principle known as weak Kőnig's lemma. So that's WKL naught. And just for historical context, this all goes back to Hilbert's program. Remember in the 1920s, Hilbert aimed to settle the question of foundations once and for all and secure modern infinitary methods, the kind of methods that were introduced by people like Cantor and Dedekind towards the late 19th century. And the idea was just to formulate these methods in formal systems and then prove the consistency of these formal systems using only kind of a safe finitistic part of mathematics. And insofar that the finitistic part is part of the modern mathematical method, Gödel's second incompleteness theorem rules that out. I mean, proof theorists look for kind of ways around that or workarounds for a while, but I think none of them are quite compelling. But so despite this setback, I'll argue that Hilbert's program, more broadly speaking, has been quite successful. So in the 20th century, people began to pursue a modified Hilbert's program. The idea is that even though modern mathematics lets you use all kinds of infinitary methods, most mathematical arguments don't require the full strength of axiomatic set theory. I mean, you can get by with less. And so, what you want to understand is, for different parts of mathematics, how much of the infinite are you really using? How much do you really need? And then trying to understand those portions of mathematics in terms of their combinatorial and computational consequences, right? So you sort of try to find subsystems, weaker theories, weaker axiomatic theories than set theory that suffice to formalize interesting parts of mathematics, and then you try to sort of mine those theories for interesting combinatorial and computational properties, and the result was, as I said, fairly successful. In the 20th century, we learned that you can interpret a lot of mathematics and theories that are not very strong. And moreover, you can find informative and interesting computational and combinatorial characterizations of their strength. The computational characterizations of their strength have informed developments in computer science in various ways, a little bit less so in mathematics, but there have been interesting combinatorial principles that have had independent mathematical interest. And so, in terms of formalizing theories in weak subsystems, there are a lot of different frameworks, but one of the most sort of useful and fruitful ones has been subsystems of second order arithmetic. And in terms of methods of analyzing them and reducing them to computational and combinatorial principles and so on, there's a whole host of techniques. There are double negation translations and ordinal analysis and realizability and functional interpretation and things like that. So specifically, the theorems I'm going to be talking about today are these. So first of all, I'm going to tell you that I sigma 1 is a pi 2 conservative extension over primitive recursive arithmetic. Right? I'm going to tell you what, I'm going to give you the definition. I'm going to tell you what all these means, but this is just a quick preview. So there is conservation of I sigma 1 over PRA, but there's speed up involved. So when you translate proofs from I sigma 1 to primitive recursive arithmetic, there's, in some cases, there's necessarily a dramatic increase in the length of proof. On the other hand, RCA naught is interpretable in I sigma 1, and hence pi 1 conservative over it. And in this case, it's an interpretation. So there is no dramatic increase in the length of proof. I will also tell you about Kőnig's lemma and a celebrated theorem due to Friedman from, I think, when was it? Around 1980. Maybe somebody can chime in if they know the date, but it goes back a while. As that WKL naught is pi 2 conservative over primitive recursive arithmetic. And that was followed by a strengthening due to Harrington, which is that WKL naught is pi 1 conservative over RCA naught. And with the prior reductions of RCA naught to primitive recursive arithmetic, that gives Friedman's theorem as a corollary. But one of the results in my dissertation, which was discovered independently and before me, in fact, by Hayek, is that there are ways of interpreting WKL naught in RCA naught. So in that case, there is also not a dramatic speed up in the conservation result. And so, when you put it all together, what do you get? Well, I mean, the idea is that you can carry out interesting mathematics in WKL naught, and related theories, right? So it's sort of an interesting portion of mathematics is represented there. And so, the fact that you can reduce them to primitive recursive arithmetic seems to tell us something interesting about the logical strength of common patterns of mathematical reasoning. Okay, so ordinary branches of mathematics. Also, the fact that you can kind of eliminate compactness and in some cases, in fact, extract primitive recursive functions is fundamental and central to Kohlenbach's proof mining program, which aims to do this to mathematical arguments in concrete cases. Okay, so yeah, so I've given that a quick overview. So what I'm going to do is I'm going to go through and state all the results now in more detail. I'm going to tell you what the theories are and tell you what the statements of the theorems mean, and then I'm going to talk specifically about an interpretation of WKL naught and RCA naught. So yeah, just on a personal note, so as I said, the fact that there was no speed up between WKL naught and RCA naught is one of my first publications. And now, as Tom mentioned, I'm about to send a textbook off to Cambridge University Press. And in that textbook, I wanted to find a proof of this result. But I wanted it's an elementary textbook, so I didn't want to have to build up a whole lot of machinery and so on. So this prompted me to find the nicest proof that I could find of the result, and that's what I'm aiming to get to today. So just to kind of flash the table of contents in front of you. So here it is. Here's the draft, and it's just it's just a meat and potatoes mathematical logic textbook, but with a syntactic proof theoretic bent. So it's propositional logic and semantics of propositional logic.
Can't read it.
I'm sorry, what, Paul?
A bit bigger, please. Can't read it.
Oh, bigger, yeah. Sorry, yeah. Let me do. Let me see if I. Yeah. How's that? Yeah, I mean, I don't want to dwell on this. I just wanted to wave this in front of you. But it's propositional logic, then first order logic, semantics of first order logic. But you know, cut elimination has a prominent place. And then standard properties of both classical and intuitionistic first order logic. And as much as possible, I try to give both syntactic and semantic arguments. A lot of time talking about primitive recursive functions and what they can do, and primitive recursive arithmetic and what it can do. First order arithmetic and fragments of first order arithmetic and some of the standard conservation results. Computability, so I'll talk about some of that today. The incompleteness theorems, simply typed lambda calculus and combinatorial logic. And then, arithmetic and computation, so realizability interpretations and dialectic interpretation. Second order logic and arithmetic, subsystems of second order arithmetic, and then foundations. So that's what's there. I haven't sort of made it public just because I'm still going through and looking for for bugs and typos and so on. So I'm trying to kind of avoid kind of a proliferation of buggy copies out in the wild. But if you do, so I have them in a Dropbox. So if you do want if you do want access to take a look at a copy, just send me an email. I'd be glad to send you a link to that. Okay, so okay, so yeah, so here are the theories. So primitive recursive arithmetic. Let's see. Wait. Oh, sorry. So to talk about primitive recursive arithmetic, so you have to know or remember that the set of primitive recursive functions is the smallest set of functions from the natural numbers to the natural numbers of various arities, containing zero, successor, and projection functions, enclosed under composition and primitive recursion. So I'm thinking of constants as just being zero-ary functions which take no arguments. So that just turns out to be convenient for the definition. But it's just it's a very meager schema for defining functions. It's it's some piddly little starting functions, composition, and just the simplest principle of recursion that you can imagine on the natural numbers. And primitive recursive arithmetic is just a formal axiomatic theory designed to go with it. So the canonical way of presenting it is as a quantifier-free calculus. So you say that 0 is not the successor of any number, and the successor function is injective. And you define, you add the defining equations for the primitive recursive functions. So it's basically just, well, not this one, but the projections and composition and primitive recursion. And then a principle of induction for quantifier-free formulas. So you formulate it as a rule. If you can prove that some formula holds of 0, and whenever a holds of x, it holds of x plus 1, then it holds of an arbitrary term. And this seems like a toy model of computation and a toy axiomatic theory. Surprisingly, well, maybe not, I don't know. Surprisingly or not, it turns out that all reasonable computable functions are primitive recursive, and all reasonable facts about them can be proved in primitive recursive arithmetic. And in the book I just show you, I spent a couple of chapters really working hard to make this claim compelling. Any reasonable statement about finitary objects, if it's mathematically provable and you can prove it, combinatorially, right, in finitistic terms, just talking about finite objects, it's going to be provable in primitive recursive arithmetic. Okay. And in fact, it turns out empirically to be surprisingly hard to find ordinary mathematical theorems that can be stated in the language of primitive recursive arithmetic, but not proved there. Right. The only counterexamples we have are those that are cooked up by logicians, to be explicitly, not provable in PRA. It's really hard to find mathematical statements in the wild, mathematical theorems in the wild that can be formulated as theorems of primitive recursive arithmetic, but not proved there. So you should think of primitive recursive arithmetic as a robust theory for reasoning about finite objects. So first order arithmetic, the way to think about it is primitive recursive arithmetic plus induction. So there's a classical version and an intuitionistic version. And you can interpret the classical version and the intuitionistic version with the double negation translation. Usually, arithmetic is formulated in a much smaller language. But the idea is in that language, you can define the primitive recursive functions and prove their totality and reason about them that way. Okay. And we will care about the complexity of formulas. So we'll say a formula in the language of arithmetic is delta naught if every so basically there are no quantifiers except for quantifiers that are bounded. So think of the delta naught formulas as being really kind of explicitly finitely checkable properties. And then we'll care about sigma-1 formulas, which are delta naught formulas preceded by some existential quantifiers. So think of those as making existential statements. Pi-1 formulas making universal statements, and then delta-1 are, delta-1 are the things that are both. So we'll get to this soon, but in terms of computability, the sigma-1 definable properties are the ones that are computably enumerable. These are co-computably enumerable, and these are computable. And so, since the primitive recursive functions are computable, they have delta-1 definitions. And so you can reason about them in the language of arithmetic. Right? And so, the first result that I need to tell you about is that if you restrict Peano arithmetic so that you only allow the induction principle for sigma-1 formulas, then you get a conservative extension of primitive recursive arithmetic for pi2 sentences in the following sense. If I sigma-1 proves that for every x there is a y such that a of xy holds for some delta naught formula a, then there's an explicit function symbol f such that primitive recursive arithmetic proves that for an arbitrary x, a holds of x comma f of x. And so this theorem is due to Parsons, Mintz, and Takeuchi independently. I like to tell the story that in the late 90s, I attended a meeting at Oberwolfach where I mentioned this result, and I referred to it as Parsons' theorem. And Parsons wasn't there in the audience, but Mintz and Takeuchi were. So it was my first professional faux pas, and they were absolutely gracious and wonderful about it. And so it was just wonderful talking to them at the meeting. So really, it's really due to the three of them independently. And by now, there are lots of ways to prove the theorem. So in fact, Parsons used the dialectic interpretation. But so Takeuchi and Mintz in different ways used code elimination, but they're syntactic proofs. There are also model theoretic proofs. There's a model theoretic argument due to Friedman. There's another one that I quite like that's in the book. So yeah, there are different ways to get the result. But there's another important relationship between I sigma 1 and PRA, which is that in the conservation result, there's a speed up involved, right? So there's a polynomial P and a sequence of quantifier-free formulas, A0, A1, up to AN minus 1, such that for every n, there's a proof of the formula AN. Oh, that should be I sigma 1 of length P of n. So there are polynomial size proofs of these formulas in I sigma 1. But yet the smallest proof of AN in primitive recursive arithmetic is, has length a stack of 2. So this is 2 to the 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 0. So it's an iterated exponential. And so the proof is, I think, first, explicitly written down by Alexander Ignatovich. But he used Solovey, a method due to size. So Solovey had done a similar proof to show a similar result for the conservation of Gödel-Bernay's set theory over Zermelo-Frankel set theory. The idea is, again, that I sigma n, I apologize, should be I sigma 1. The idea is you use, there's a clever way of using I sigma 1 to prove consistency of very large fragments of primitive recursive arithmetic. And I should mention that John Burgess, who's a philosopher at Princeton, has pointed out quite correctly that this speaks against thinking of this as a finitistic reduction. So if you're a finitist, and by that you mean you believe in, in primitive recursive arithmetic and nothing else, well, if somebody gives you a proof in I sigma 1, well, that's all well and good. The proof, the reduction, is the proof. The theorem I just showed you is finitistically acceptable. So as a finitist, if somebody gives you a proof in I sigma 1, as a finitist, you know that there's a proof in PRA, but that proof can be really, really long. And knowing that there is a proof in PRA doesn't tell you that the result is true if you're a finitist, right? On top of that, you need this extra reflection principle that says, oh, and moreover, anything I can prove in PRA is true. Right? So either you have to unwind the proof and get a proof in PRA, but that might be way too long, or you need a reflection principle that goes beyond finitistic reasoning. And I think that's a valid point. It's still, an interesting result. It says that, okay, so, but still, you can translate the, you can use this as an instrument to get results if you accept, finiticism, plus a little bit more, like a reflection principle, or the various other ways of sort of, getting the extra strength. I mean, if you're really hardcore finitist, you might want to just give up sigma 1 induction. It does give you a recipe for the translation, and in practice, when you actually apply it to particular results, the speed up might not be nearly that bad. But even setting the finitistic reduction aside, it does tell you that anything you can prove in any for all exist statement you can prove in I sigma 1 comes with primitive recursive bounds, and that's sort of an independently interesting property. Anyhow, second order arithmetic. So in addition to variables ranging over natural numbers, you have variables over sets, and you can say that something is an element of the set. You have induction extended to the bigger language. Now you can quantify over sets as well as numbers. And there's a comprehension principle that says that every formula defines a set. Right. So the standard model is just, you have the natural numbers and the collection of all subsets of natural numbers. Right. So that's full set of second order arithmetic. And second order arithmetic is from a proof theoretic perspective, it's really very strong. And so for a modified Hilbert's program, you want to consider weaker subsystems. And you can do that by restricting the comprehension principle. So say that, look, I'm going to have less than full set comprehension, or restricting the induction principle. Or you can do, both, or combinations of both. And so subsystems of second order arithmetic is just what the name says. It's the study of weaker fragments of full second order arithmetic. And the big five theories of reverse mathematics I've listed there. So RCA naught, WKL naught, ACA naught, ATR naught, and Pi11CA naught. And in this talk, I'm going to focus attention on the first two, RCA naught and WKL naught. So those are the ones that are relevant to our story today. So the axioms of RCA naught are just the quantifier-free axioms for 0, successor, plus, times, and less than. Induction for sigma 1 formulas, where you're allowed to have set variables now. So it's like I sigma 1, extended to the bigger language. But what you do is you weaken the comprehension principle to one that says roughly that computable sets exist. It says that if you have a sigma 1 description of a set and a pi 1 description of a set, and you know that they're equivalent, right? So you have an equivalent sigma 1 and pi 1 formula, then there is a set whose elements are the ones that satisfy those formulas. So there is a set Y such that for every x, x is in Y if and only if A of x holds. Okay. And let's see. Yeah, I think I'm going at an okay pace, right? And notice that, when I say you have induction for sigma 1 formulas, that includes a principle of induction just for sets. For every set Y, if 0 is in Y and Y is closed under successor, then everything is in Y. But because we've weakened set comprehension, saying that you have induction for sigma 1 formulas is a little bit stronger than just taking set induction. Okay. And since RCA naught includes I sigma 1, and I've told you that I sigma 1 interprets primitive recursive arithmetic, it's also convenient to think of RCA naught as including primitive recursive arithmetic. Okay. And so the way to think about RCA naught is simply this. So it says, as I said, the axiom RCA, recursive comprehension axiom, says that a set exists if it has a CE and a co-CE definition. Okay. And so that roughly allows you to define computable sets and relations. So the smallest omega model of the theory is, you just take the first order variables to range over the natural numbers, and you just take the second order variables to range over the computable sets. Right? So that gives you a model of the theory. And so you can think of RCA naught as just a formal theory for reasoning about numbers and computable sets. Okay. And in this case, it's straightforward to interpret RCA naught in I sigma 1. Because as I said, you can think of the set variables of RCA naught as ranging over computable sets. Well, a computable set is given by a Turing machine, or some index for a Turing machine, or an index for a computable function. So roughly in I sigma 1, you can interpret RCA naught by interpreting the set variables as ranging over numbers representing indices for computable functions. Okay. And you have to be careful to state that precisely and describe the translation. But it's it's the kind of thing that proof theorists do straightforwardly. Right? So it's just a translation. Okay, so let me kind of take stock of where we are. So I've told you primitive recursive arithmetic is, you want to think of it as just a robust theory of finitistic reasoning, in the sense of Hilbert and Bernays. I sigma 1 is an extension of primitive recursive arithmetic with an extra principle of sigma 1 induction. It's pi 2 conservative over primitive recursive arithmetic. So there's a sense in which it's not stronger, but it is more efficient. There's speed up in going from I sigma 1 to PRA. Then RCA naught is pi 1 conservative over I sigma 1. So in particular, any formula in the language of I sigma 1 that's provable in RCA naught is also provable there. And in this case, it's just a direct interpretation. There's a direct translation. Okay. Which means that all I have left to do to sort of set the stage for the results I want to talk about is I need to tell you about weak kernel WKL naught, and then I'm going to tell you about why it's pi 1 conservative over RCA naught. Okay. So to tell you about WKL naught, a binary tree is a collection of binary sequences closed under initial segments. So there's a finite binary tree, right? So there's the empty sequence and 0, 0, 0, 0, and 0, 1. Right? So being closed under initial segments that if 0, 1, 0 is in it, then 0, 1, and 0, and 1 have to be in it. Okay. And since formal theories of arithmetic, we can represent binary sequences as numbers, right? We can think of a tree as being a set of numbers. Trees can be finite or infinite. A path through a binary tree is a maximal set of compatible nodes. So in this tree, that's a path, and then there's another one, and then that's another one. So there are 3 paths through this tree. An infinite path you can think of as being in one-to-one correspondence with an infinite binary sequence, right? Just the sequence of all the numbers that get you through the tree. And you can think of that as being the characteristic function of a set of numbers, right? So you can represent it in different ways. So every infinite, so it's a consequence of König's lemma, or it's an instance of König's lemma, that every infinite binary tree has an infinite path. You just step through the tree maintaining the property that there are infinitely many descendants, right? So if you think of this as being an infinite binary tree, you think of there being more stuff below. If I tell you that it's infinite, that tells you that one of the 2 subtrees has to be infinite. Say it's the left one, you go left. Knowing that this subtree is infinite tells you that one of the 2 children of that have to have infinitely many descendants below it. And you just kind of walk through the tree, right, maintaining that property. Okay. And König's lemma just says that every infinite binary tree has a path. So it's the formulation of König's lemma for binary trees. So you can say that something is a tree by saying that for every pair of binary sequence sigma tau, if tau is in the tree and sigma is a subset of tau, then sigma is in the tree. You can say that the tree is infinite by saying that for every n, there's something in the tree of length n. Right? There's some node at the nth level. I said that you can think of a set of numbers p as being as representing an infinite branch, right? So think of a finite sequence sigma as being an initial segment of p. If the bits of sigma track membership in p, so for every I less than length of sigma, I is in P if and only if the corresponding bit of sigma is 1. And then saying P is a path through T says that every initial segment of P is in T. Okay. And so weak König's lemma is just the statement that every infinite binary tree has a path. Okay. And WKL naught is RCA naught plus weak König's lemma. We'll see in a moment that there are computable trees with no computable paths. So the smallest model of RCA naught, the smallest omega model of RCA naught, isn't the model of weak König's lemma. So RCA naught doesn't prove WKL. But the very nice result by Leo Harrington is that it's a pi11 conservative extension. So in particular, any arithmetic statement that's provable in WKL0 is also provable in RCA0. Okay. And mathematically, the interest of Kőnig's lemma is that it is a form of compactness. So in reverse mathematics, you can show that over RCA0, it's equivalent to various compactness principles or things that require compactness. So the Heine-Borel theorem for the unit interval, or the compactness principle for Cantor space, or the statement that every continuous function on the unit interval is uniformly continuous, or that it's bounded, and so on. Okay, so I'm looking at the time. I've got about 10 minutes left. So in the time I have left, I'm just going to do everything I can to tell you why WKL0 is pi11 conservative over RCA0. Give you at least a picture of why that result holds and why you can actually turn it into an interpretation. So before I do that, I'm going to get a sip of water and ask, I've been talking for a while. Are there any questions, or is there anything I can clarify? Kind of flip through.
I just have a very minor question, Jeremy. When you say pi11 conservative over I sigma 1, you're formulating the latter with set variables or something.
Yeah, I'm being really sloppy here, but yeah, so what you want to do is, what you want to say is, if you take a version of I sigma 1 where you throw in like a free set predicate and so on, any pi11 statement provable in RCA0, the corresponding matrix with that free set variable can be proved in I sigma 1, with that extra thing.
Okay.
Yep. Yeah, I was trying to gloss over the details, but yeah, you got me. All right, anyone else? Okay, so let's get to the story, right? So Harrington's original proof of the conservation of WKL0 over RCA0 was a forcing argument. The idea is, you start with a model of RCA0. As I said, there might be infinite binary trees with no infinite path. Well, you want to just sort of take a path and just throw it into the model, right? So you want to pick a set X, pick a path through T and add it through well, you want a model of RCA0. So if you throw in X, you want to throw in all the sets that are computable from it in the sense of the model. The problem is that can break some of the axioms, right? In particular, if you do that, now you have sigma 1 formulas that now can, refer to that new object you added. And there's no reason to think that sigma 1 induction will still hold. Okay. And so the forcing idea is to add a generic path through T, pick a very nice path through T, and one that will preserve sigma 1 induction. Okay. And the way I like to think about forcing arguments, so Dolly Parton, likes to go out saying, it cost me a lot of money to look this cheap. In a forcing argument, what you want to do is you want to add a generic path through a tree, or in this case, you want to add a generic object, one that just is really almost unnoticeable, has no distinguishing properties. And you work really, really hard to add, to construct something that's really kind of almost invisible. It just doesn't have these any properties. So the idea is you want to build the path through the tree T with a sequence of approximations. And you want to do it in such a way that the only properties that it has at the end are the things that it had to have at some finite stage of the construction, right? I mean, intuitively, you want to make it so that nothing holds of this tree. It has no properties at all, except for the properties that it had to have just because of the construction. Okay. And if you do that, because a sigma 1 property of the thing at the end, I mean, that's a property. You can reason that, well, if it has a sigma 1 property, it has to have it because of something in the construction. And that's something you can describe in terms of the original model. Okay. And that adds sort of one path through a tree. And then you just keep going, just keep adding them. Okay. Okay. So let's see. So, if you think, yeah, I don't know how far I'll get through the argument. I'll just keep going and then sort of try to find a good stopping point. But to give you a sense of what's going on. So first of all, let me sort of tell you why there are computable binary trees with no computable sequences. So because we're thinking of a tree as just a set of binary sequences, and a binary sequence we can code as a natural number, right? A tree is just a set of numbers, and it may or may not be computable. So it's a theorem that actually goes back to Kőnig that there's a computable infinite binary tree that has no computable path. Okay. And so let me tell you or remind you that a set is computably enumerable if it's the range of a computable function. So you have a computable function phi sub e that whose outputs give you the elements of the set. And being computably enumerable, as I said before, is exactly the same as being definable by a sigma 1 formula. Right? So there's a theorem. It's kind of it's almost a homework exercise for students that you can find two computably enumerable sets A and B such that there's no computable separation of them. In other words, there's no computable set C that contains A oh, did I get it right? Who's right? Sorry, that contains A and whose complement contains B. Right? There's no computable set that separates A from B. And the proof is just to exhibit them. If you take A to be the set of natural numbers n, such that the nth Turing machine halts on input n and outputs a 1, and you let B be the set of natural numbers n, such that the nth Turing machine on input n halts and outputs 0. It's not hard to show that that works. It's just it's a 2 or 3 line argument, and it's in the book. Okay. And so, Kőnig's idea was to build a tree as follows. You put a sequence sigma into the tree if and only if up to the length of sigma, it looks like sigma might be a separation of A and B. In other words, you run, up to length sigma, you run, all the Turing machines up to that length for that many steps. And as long as every time one of them halts, the corresponding thing in sigma is 1, and every time one of them doesn't halt, the corresponding thing is 0. You say, okay, sigma looks okay up until this point. Okay. And you can check that gives you a tree. And then a path through tree will just be a sequence that is always consistent with being a separation, right? And that you can show that means that it actually is a separation. Okay, so you construct a tree such that any path through the tree separates two computably inseparable, computably enumerable sets. And in fact, there's a very close connection between paths through computable trees and separations of computably enumerable sets, right? So I've just sort of sketched or given you a hint that if you have two computably, I should have said disjoint computably enumerable sets A and B, you can write down a computable tree such that from any path through the tree, you can get a separation from A and B. Okay. Going the other way, if I give you I should have said a computable infinite binary tree, there are disjoint computably enumerable sets A and B, such that a path through T can be computed from any separation of A and B. Okay, there are bugs on this slide. I'll go back and separate it. But the short story is you can compute paths through infinite binary trees from separations of disjoint computably enumerable sets and vice versa. Okay, and everything, by the way, I said, everything I've said relativizes. So if you replace computable by computable in X, things still work. Okay, so so Harrington was inspired with this argument by the Djakoš-Soar low basis theorem, which says that well, okay, so if X is any set, X jump, X prime denotes the Turing jump of X, which is the halting problem relative to X. It's a complete sigma 1 definable set relative to X. And the low basis theorem says that if you have a computable infinite binary tree, there's a path through that tree, such that not only can you compute that path from the Turing jump of T, but you can compute the Turing jump of that path from the Turing jump of T. Okay? And this is roughly says that any sigma 1 property relative to that path can be computed from, is basically sigma 1 in the original, is computable from the halting problem in the original tree. And the construction, it's really a forcing construction. It's an iterative construction where you build this thing in stages, and at every step, along the way, you take another step through the tree, but you try to restrict the tree so that you're guaranteed that whatever path you get at the end, the ETH Turing machine won't halt on input 0. Right? You try to guarantee that Turing machines just won't halt. And so if you can do that, you do. And at the end of the construction, you get a path through the tree with the property that, the only Turing machines that, halt on empty input relative to the path are the ones that were forced to halt at that stage of the construction. So that's what sort of gives you the control over sigma 1 properties of the path from the construction itself. And let me go on for another 3 minutes and see if I can get a quick impressionistic sketch of the idea. So translated to the language of second order arithmetic, this says roughly that you can expand any model M of RCA naught by adding a path through a tree and still preserve sigma 1 induction. Okay. And so to turn this into an interpretation of WKL naught, so this gives you a way to add a single path. But if you want to get pass through all the trees in the model, then you have to iterate and keep going. And if you want to turn this into a translation of WKL naught into RCA naught, you need to carry out the iteration internally. So Hayek's construction, he used a universal construction, but he still needed a fiddly iteration. In my dissertation, I internalized the forcing argument and used an iterating forcing argument. But in 2016, Tin-Lock Wang gave a very nice proof of the conservation of, and an interpretation of WKL naught in RCA naught, which used an arithmetized version of the completeness theorem that sort of avoided the iteration entirely. Right? You could just sort of use weak Kőnig's lemma, use a path through a tree to get a model of arithmetic. And in that model of arithmetic, you could from that you build a model of WKL naught. And the proof I use in the book is basically a combination of Hayek's recursion theoretic argument and Wang's approach. So let me just state the two. Let's see. Yeah. Let me just kind of state the two results that put together do it, and then I'll stop there. Right. So the idea that Hayek used in his construction is that there's a universal infinite binary tree. Right. So in other words, you can write down a single computable infinite binary tree with a property that if you have any path through that binary tree, you can get a path through any other computable infinite binary tree. Right. So there's one infinite binary computable tree that's as hard as any to find a path. Right. If you find a path through that one, you can find a path through any infinite binary computable tree. And that's not a hard or surprising thing. That's just the kind of thing that one does in computability theory. You have just a universal construction, right? And that doesn't quite give you what you need for the construction, because that says you can add paths through all the computable binary trees, but then you have to add paths through the trees that are computable from that path. Right. And then you have to add paths through the trees that are computable from those paths and so on. So Hayek still needed an iteration. But the magic trick that does it, and this is what's in the book, is that you can actually write down one tree such that a path through the tree gives you a full model of WKL naught. Right. So a model of WKL, an omega model of WKL naught, is just a collection of sets that's closed under pairing and Turing reduction and paths through infinite binary trees. And the magic trick is that there is a single computable infinite binary tree such that if you have any path through that tree, then from that path, or that path in fact is or codes or represents a sequence of sets, that's an omega model of WKL naught. And once you have the idea to do that, the proof is very easy. You just sort of write down what P has to do. Okay, so it's the only hard part of the theorem is thinking that this is what you need to do. Okay, and so stating this theorem, proving it, and then formalizing it gives you exactly an interpretation of WKL naught and RCA naught. And I should mention that after I discovered this to put in the book, I asked around, and Denise Hirschfeld told me that in fact this theorem has been known for a few years in the computability theory literature. I mean, it's been around, it's been used for various things. But then he said to me, oh, but it never occurred to me that you could use this to prove the conservation of WKL naught over RCA naught. So it was just kind of satisfying that after all these years to finally come across the proof that that I should have. Oh, I'm sorry, there's a typo there. Binary. This is the proof that I should have done in my dissertation, and so now it's the proof in the book. So that's it. So this is a good place for me to stop. So I'm sorry I rushed through the last few slides. And in questions, I'm happy to say a little bit more about the construction. But hopefully, at least, even though I went quickly, I at least gave you a flavor of the argument and a sense of the results. So thanks very much.